The third talk in the afternoon will be presented by Professor Minkyu J. Professor Minkyu J is from KAIST. He received his bachelor and master and PhD degree all from KAIST. In 2003, he joined Samsung Electronics. From 2006 to 2013, he was with A-Star in Singapore. And he was an associate professor in the Department of Information and Communication Engineering at Daegu Junbok Institute of Science and Technology from 2014 to 2015. And then he joined KAIST since 2016. His main research areas are advanced IC platform development, including smart sensor interface ICs, ultra-low power wireless communication ICs, high-efficient energy supply and management ICs, ultra-low power timing ICs, resource-constrained computing ICs, as well as microsystem integration leveraging the advanced IC platform for emerging applications. I think that's why you need 40 PhD students. Okay, let's join me to welcome Professor Minkyu J.
Hello, good afternoon. I'm Minkyu J. I'm very happy to be here. So thank you for having me here so that I can have a chance to give my talk to my friends and students here. So today I will talk about the building neural interfaces, the key components, system integration, and technical hurdles. Okay. So this is the outline of my talk. So first, I will start with various applications of the neural interfaces and its system structures. Okay. So if we look at the applications of implantable neural interfaces, we can think of two main categories. So the first one is neurotherapeutics for treating the neurological disorders like Parkinson's disease and epilepsy, chronic pain, and the bioelectronic medicine for dealing with metabolic and immune diseases. Okay, and another category is neuroprosthetics for restoring the neurologically impaired body functions for the patients suffering from paralysis or visual and hearing impairment and the limb amputation. Okay. So here we can see the generic structure of the fully implantable neural interface system. So I will explain this generic structure first, one by one. So at the center, we have this neural interface system on chip. So I will explain in more detail later. This is the major focus of this talk. But together with this neural interface system on chip, we obviously need electrodes and other sensors and actuators like recording electrodes, electrochemical sensors, photodetectors, stimulation electrodes. Sometimes we also use ultrasound transducers or laser emission diodes, right? We need some coil or other types of power transducers in many cases, such as a coupled coil, ultrasound transducer. So sometimes we transmit the power using ultrasound wave, acoustic wave. And we can even use electrode for body coupled powering. And recently, researchers are working on these magnetoelectric transducers as well, right? And in many applications, we still need some small battery there. It should be biocompatible, of course. And for communication, we need antenna or other communication transducers like the normal antenna or coupled coil. And we also communicate using the acoustic wave. And we can use electrode for electrical field-based communication through the human body. And the magnetoelectric transducer can be also used for data communication. All right, so now I will explain this neural interface system on chip inside. So we can find this neural interface front end first, right? So this front end can have neural recording circuits as well as neural stimulation circuits. And coming to this signal processing, so it plays quite a diverse role, like data compression, diagnosis, decoding, interpretation, detection, prediction, and sometimes even on-device learning for the patient-specific treatment, right? Coming to the wireless data communication, of course we need the wireless transmitter and receiver. And for power management, we need the circuits for wireless power transfer as well as battery management in many cases. Okay, so from now I will explain how this generic structure can be varied to be applied for different applications. Okay, so let's think of this first example, which is deep brain stimulator for Parkinson's disease, right? So usually this traditional deep brain stimulator device is stimulation only. So it doesn't have a recording front end. It is lying on the neurostimulation front end, working together with some depth electrode for deep brain area stimulation. And we usually have a handful of electrode there, so low electrode count. So that is a kind of a feature of this type of device. And it is operated by battery, and the traditional one is relying on the manual device programming without any wireless programming, the automatic intelligent programming feature. So we use this wireless telemetry, the wireless receiver, for manual device programming. So if we look at this system, so it is pretty much like this, quite simplified, right? Yeah. And coming to the epileptic seizure treatment device, so recently the NeuroPace, the company, released a device called the RNS system, so which can operate the closed loop function to detect the seizure and suppress it in real time. So for that, it has both the neural recording and stimulation front ends to form the closed loop operation. And it still utilizes the neural signal information from the low electrode count. And it has a quite comprehensive signal processing function for on-device seizure detection or prediction. And it is still based on the battery operation. And it utilizes the wireless telemetry for device programming and also data retrieval. So whenever there is a seizure event, so it records the data inside the device, then that data can be retrieved later on, okay? Another example is the so-called electroceuticals or bioelectronic medicine. So we want to make this device so small so that it can be attached directly onto the peripheral nerve to treat a specific neurological diseases, okay? So basically it is a device for neuromodulation through the peripheral nerves, right? So of course it also realizes the closed loop operation using both the recording and stimulation function. And because this device is very small, so it cannot have a large number of electrodes, obviously. So it uses a low electrode count, and it is wireless powered using the coil or some other energy transfer transducers. And it has a wireless telemetry function as well. So in this type of device, the main challenge is with this extreme miniaturization, okay? So perhaps you heard about the Neuralink, right? So the Neuralink is the company founded by Elon Musk, developing the brain-machine interface for paralyzed patients at the first stage. So, they dream to expand it to the even general users, not the patients, but at this stage, they are pretty much focused on the paralyzed patients. So it is recording only, so they are not really taking care of stimulation side yet. But because it has to interpret the human intention, so I mean, more generally speaking, it is kind of reading the mind. So usually it requires a large number of electrode, right? So that should be the challenge of this type of system. So because it is dealing with recording the signal from the huge number of electrodes and processing the signals from those electrodes, so it cannot be operated using only the battery. So the battery lifetime will be very limited. So it is usually combined with wireless power transfer. Okay, and also their challenge is also with the wireless telemetry, especially the transmitter side, because it has to communicate the huge size of the neural recording data throughout the antenna or some other communication transducers. And it also wants to provide a quite sophisticated signal processing function inside, so that we can perform the on-device signal decoding, interpretation, compression. So for all these signal processing functions, it requires large-scale data processing. Okay. So retinal implants or cochlear implants can be other examples and significant examples, right? So it is for the disabled patients suffering from the hearing or visual impairment. So basically, it is evoking the visual or audio sensation through the electrical stimulation. So traditional device is based on the stimulation only. And to provide a more natural and more sophisticated sensation, they are evolving toward higher electrode count. So the old device has a low electrode count, but they are increasing the number of electrodes more and more. So because of this increased number of electrodes, for the stimulation throughout this large number of electrodes, it requires some wireless powering on top of the use of battery. And in this case, actually, the data communication challenges with this receiver side rather than transmitter side, because it has to receive a huge size of the audio or video data so that it can perform the neural stimulation according to that video or audio data. Okay. So, and also because it is fully implantable, so it has to rely on only one single coil for simultaneous wireless power and data transfer. Otherwise, the device form factor will be too large and too much invasiveness will be resulted. So how we can transfer, communicate large size of the audio and video data, and also transfer the sufficient amount of the power at the same time using one small single coil. So that is a challenge of this type of system design and implementation. So finally, the prosthetic limb is for the patients have the limb amputation. So basically, it records the motion intention signal from the peripheral nerves, and using that information, it will actuate this prosthetic limb. So basically, it is a recording only, but for the sophisticated signal processing, it requires a signal from a large number of electrodes. And so it also requires a wireless powering on top of battery. And in this case, high TX data rate is required because it records from large number of electrodes, and we want to process it outside in many cases. So we need this high data rate transmitter. And of course, this device also tries to implement some on-device signal decoding and interpretation. Then actually we can reduce the size of the data we have to transmit out as well. Okay. All right. So I know I don't have much time, so I will accelerate. So I want to just discuss two things. So component level challenges and system integration challenges. So after that, I have some interesting neural interface system examples, but I don't think I have time to cover that. But just to share the recent research directions and research trend, I will focus on delivering these two topics from now. So I will cover it quickly. So coming to this neural recoding circuit block, so requirements are like this. So as we all know very well, low noise, low power consumption, because we know very well, I will skip it. I will not explain too much details. And H-coupled input, because whenever we have electrode, between the tissue and electrode, we have a unexpected amount of DC offset, so we need AC coupling in the input. And there is a large common mode interference, like stimulation artifact or the motion artifact, so we need a high common mode rejection ratio, right? Otherwise, our weak differential recording signal will be easily distorted and saturated, okay? And high input impedance is also important because we want to minimize the conversion of common mode interferences into differential mode input components, right? So even if we have a high common mode rejection ratio, if there is a mismatch in the two electrodes we are recording, then the portion of the common mode interference signal will be converted to the differential mode signal. But if we have a very large input impedance, we can avoid this problem, right? So, and another important requirement is a wide input timing range, right? So, of course, we are trying to have this high input impedance as much as possible, but it cannot be perfect. So, still, we will have some CM to DM converted interference signal. So, then we have to accommodate the converted interference, right? So, to accommodate it, so we need some extent of input timing range. Otherwise, we will have a lot of problem especially in the closed loop applications where we have to record while stimulating at the same time, right? Okay, so far what I mentioned is kind of the important requirements and challenges many people have already worked on to address, but these are kind of more recent challenges and requirements, I would say. So small area consumption, right? Because now quite a few companies are working toward the scalable brain-motion interface. So we really have to increase the number of electrodes drastically, right? So now we can record from about 1,000 electrodes, 1,000 channels, but obviously it is a low number to understand the human intention and human mind, right? So it may be, we may need to increase this number to like millions, right? Perhaps beyond millions. So, but now we can only record from thousands, right? So there should be huge scale of the increase in terms of the number of channels and electrode. So for that, we really need a scalable recording front end. So we need a scalable technology for neural interfaces. So small area consumption will become more and more important. And at the same time, the people want to obtain a more comprehensive understanding of heterogeneous population of neuronal cells. So rather than recording only the electrical signals, we want to record the signals in other domains as well. So optical domain and the electrochemical chemical domain, whatever. So multimodal recording will be another very important research trend. Okay, so neurostimulation. So high stimulation efficacy, high energy efficiency, and patient safety are very obvious, right? So especially for patient safety, the usually neurostimulation front end requires the charge balancing function, right? So that we can minimize the residual charge after consecutive stimulation pulses. So we can guarantee the patient safety so that we, by avoiding the tissue damage. And of course, this charge accumulation can result in the electrode corrosion as well. Okay? And to guarantee the sufficient stimulation current delivery, even when the impedance between the electrode and tissue is quite high, so we need to provide the high voltage compliance. And again, for more scalable neural interface front end for the future applications, perhaps, most probably, the number of stimulation channels will be smaller than the number of recording channels, but to some extent, the stimulation front end should be scalable as well. So how we can minimize the area consumption will be important challenge for neurostimulation front end as well. Because especially for neurostimulation, in many applications, we need high voltage compliance, right? So then we need a high voltage device used. So while supporting the high voltage compliance, how we can minimize the area consumption, that will be quite important research subject. And another interesting research direction is localized and selective stimulation. So we want to minimize the unwanted stimulation other than targeted neurons and nerves, right? So we don't want to excite the neighboring neurons and nerves so that we can maximize the stimulation efficacy, and also we want to minimize unwanted side effects, right? So this localized and selective stimulation will be another important research direction. So coming to wireless power transfer, so we have to be able to deliver sufficient amount of power. So high power delivered to load, high power transfer efficiency, obviously important. And we should be able to cover sufficient power transfer distance. And if we can deliver sufficient amount of power with sufficiently high efficiency with an even smaller coil, that will be even better. So how we can reduce the size of coil will be another important research topic. So these days, our research group is also working on the simultaneous power and data transfer using a very small single coil link. Okay, so this will be interesting research topic continuously. So wireless data communication. So we need high data rate in many applications, especially for brain-machine interface, and high energy efficiency, high spectral efficiency. They are all important. And we need to provide sufficient TX output power so that we can guarantee stable communication over required distance, and sufficient receiver sensitivity to guarantee stable communication over required distance. And again, the small size antenna for miniaturization will be another important research direction. So finally, the signal processing. So high processing accuracy, low power consumption are important. And the sufficient processing throughput and latency to process a large amount of data for the scalable system with a sufficient speed and latency. And a small amount of processed output data to ensure no excessive burden to the following wireless communication function. So when we increase this number of electrodes for scalable brain-machine interface, so even if we improve our wireless transmitter technology further and further, eventually we will face the limit, okay? So to overcome that limit, we have to combine our wideband data transmitter together with this on-device signal processing function so that we can reduce the amount of data we have to transmit, okay? All right, so I covered the component level challenges. So finally, I will talk about the system integration challenges. It will be a shorter one. So upscaling, as I already mentioned, right? So upscaling will be quite hot research topic for a while. And coexistence. So recording channel performance affected by stimulation artifacts in the bidirectional neural interface system. So how we can mitigate this issue will be interesting topic. And cross interference between the wireless power and data links will be also interesting research topic. And the miniaturization, so how we can maintain the wireless power and data link performance while using the small coil and antenna, and how we can operate the device with a very, very small battery. So those topics are related with the miniaturization of the system. And finally, the biocompatibility and safety is, as you know, very important prerequisite for all the implantable medical devices. Right, so I have a review of some examples, but I will just skip it. So I will share this slide, so you can just take a look at it if you are interested. Right, so finally, the summary and conclusion. So neural interface systems are used for various important neuroprosthetic and neurotherapeutic applications. So the implantable neural interface systems share a generic structure consisting of key components, as I already explained. So this generic structure is buried into different combinations of key components for different applications. And each key component should be designed to meet its own requirements. And there are component level challenges which have not yet been addressed sufficiently. And there are important challenges facing the system integration as well. And the novel neural interface system designs have been proposed incessantly to address these challenges, and people are still working on it. So I hope this presentation was useful for your future research in this field. Thank you.
Thank you, Minkyu. This is a very complete summary of his work. So, do we have any questions from the audience? Yeah, let me ask you one of them.
Yeah.
You mentioned about high voltage stimulation.
Yes.
Right. So, what's your opinion? Should we use high voltage devices, or we just stacking many low voltage devices?
So if you don't have a area restriction, going with the high voltage device is a safer solution. But if you really have to implement a scalable solution, then you have area restriction in this case, right?
Yeah.
Then there is no other way than using normal voltage device. Yeah.
Because of the layout of the high voltage.
Right. Yeah, but you have to put some more safety functions, overcurrent protection, whatever. Yeah.
Sure. Yes, please.
Since you mentioned this is an implantable system, okay, so how big the size do you expect in designing these systems, and what kind of process node that you use?
Okay, so it depends on the applications, but usual implantable device, the electronics is kept inside the titanium can, so which is about a half of the adult palm size. So it is not so small, it's still okay. So we can have, after packaging, a centimeter scale chip will be okay. So in terms of the technology node, we don't need a very advanced node. So, for example, if we want to put more and more digital signal processing function for the future brain-machine interface system, then we will have a huge amount of digital circuits, right? So then we may need very well scaled process technology node. But currently, I don't think we need a very advanced technology node for most of the applications. But in the future, as our neural interface system becomes smarter and smarter, we will have to move on to the more advanced technology node.
Okay. And then there was a question on
Successful your talk. I have a question because in your tutorial you give the very challenging. The challenging we need an upscale, but the size should be miniaturized.
Right. Yeah.
So I'm quite interested how can we achieve this target something. Because I think due to time limit, so you don't show some design example, but I think through the Q&A session, maybe it's a good time for Professor you can show us some example how can we achieve the upscale more channel, but we still can maintain miniaturization.
Yeah. So let me put it this way. So even if the number of electrode is scaled up, actually, of course, the chip area is also limited. But you know, a chip area is not so big compared to your power source. So actually, it is not between the number of channels and the system size. Actually, it's the trade-off more between the power consumption and your system size. Because, but as long, I mean, as we have more and more channels, our system tends to consume more and more power. But we have to make our system smaller and smaller. So that is a very tough challenge, right? So it is obvious. So then it means we need a low power design, first of all. So from the circuit, the recording and stimulation circuit design point of view and processing circuit design point of view, so we have to reduce the power consumption. But at the same time, so how we can improve the power efficiency for wireless power transfer, even using small the coil. So that will be another requirement. So we have to look at these two directions at the same time. Okay.
All right. Thanks a lot. So let's thank Professor J again.
Thank you.
Thank you.